our discussion about the SN1 reaction mechanism. And as we said, SN1 reaction mechanism, just very quickly about it. The SN1 reaction mechanism, it's a first order reaction, which means the rate of the reaction depends only on the concentration of the substrate in the alkyl halide, for example. Secondly, it occurs with what we call it racemization. We'll come to this in the next example. And thirdly, it involves formation of carbocation. Now, if we take the same example, what you have it in here, if you take the same example in here, for example, if we take this stereo compound, this active compound, chiral compound, take carbon here, CH3, then we have here a bromine, and then here we have like methyl. So that means this is an ethyl. So this will be CH2CH3. Now, if we allow this to react, for example, with water, which means this will proceed via SN1 reaction mechanism, what we are going to get, first of all, this here, the H2O, the nucleophile, will replace the bromine and it will simply leave OH in its place. What we are going to get, two products, simply, and approximately the percentage yield are approximately the same. So sometimes we will get the OH is above the plane and it's enantiomer where we got here so for example, if this is here, for example, what's the stereo center of this compound? This is supposed to be S. This is S. This is R. So approximately they are equal percentage what you are going to get. So approximately 50-50, which means we are going to get racemic mixture. Because as we said before, whenever we get an equimolar of both enantiomers, then we are talking about racemic mixture. So any reaction leads to the formation of racemic mixture, we call it occurs with racemization because it gives a racemic mixture. So always SN1 reaction mechanism leads to racemization. If we have a stereo center, which is, for example, certain here, for example, this is R here, right? No, this is S. This is S, right? So this is S, but here it will lead to the formation of two products, which are the enantiomers to each other and approximately the same yield, which is here in this case we call it racemic mixture. You follow me? Now, since this reaction occurs or it involves the formation of carbocation, then we should expect then different rates for this reaction and different preference. So let's talk about the effect of the substrate for the rate of the reaction, SN1 reaction mechanism. So, effect of substrate nature on the rate of SN1. Generally speaking, as you can see in the next slide here, you can see it. You can see the difference, the different aspects or the comparison. Yes, please.
أعتقد اليوم عندك مشاكل في الشبكة لأنه واضح كلنا ما واضح عندنا. يعني المثال اللي قبل ما كان واضح، الحين بس شفنا هذا المثال.
Okay, I will repeat just very quickly, but anyway, in all cases, it will be recorded, the lecture, and it will be, when I post it on the YouTube, it will be definitely more clear. But I will repeat it again. Generally speaking, SN1 reaction mechanism, regarding the previous example, the same slide actually, the same slide in here. Let me see here. Can you see the slide? Do you see the slide? Just follow the slide, which I am simply talking about. Do you see the slide, guys?
Yes, doctor.
Why the picture is sometimes stuck? Anyway, now in this slide, you can see we started up with one enantiomer, but since this reaction occurs via SN1, first of all, when we allow this alkyl halide to react with water, the water here will replace the Br and then we'll have OH. Now, since this occurs via SN1, we will have racemic mixture, so we'll have enantiomer of both. So we will get the S and the R, and that's we will have them both in approximately the same yield, and therefore we will get it actually as a racemic mixture in this case. So always SN1 reaction mechanism occurs via what we call it the racemization. You follow me? Is there any question about it? Hello? Is there any question?
بس دكتور ليش طلعوا 2 برودكت؟
Come again? شو سؤال؟
يعني ليش عندنا 2 نواتج؟
Because there is 2 possibilities here. For here you can see the water. Can you see the water here? You see the water. If there is 2 possibilities to react, either from the above side or from below side. Okay. Now, why we will get here 2 possibilities? Because this reaction, it involves a formation of carbocation. What's the geometry of a carbocation? Whenever we have carbon attached to 3 bonds and it has a positive charge, what's the geometry of it? What's the structure? What's the geometry? I can't see. What's the geometry? Let me look at here first. The geometry will be simply, it will be triangular planar, right? Do you follow me, guys?
Yes, doctor.
Right. So the triangular planar, so it will be simply, this is a planar system, which means we have it, these 3 atoms, 3 bonds are in the same plane, and this charge plus here, it's actually an empty p orbital above the plane and below the plane. So this is a p orbital, which is perpendicular to the plane of these bonds, above the plane and below the plane. Remember my words. Do you follow me? And there is a plus here. It's a plus, but of course I'm not going to write it again twice in order not to make any confusion about 2 pluses. It's just 1 plus, but for the same p orbital. Now, when we have the nucleophile here, which is in this case the water, for example, the water here, right? This is the nucleophile. The water, it will add itself. It either adds and react with the p orbital from above the plane, or it may react from below the plane. Each will give 1 enantiomer. For example, if it attacks from above the plane, it will give R. If it attacks from below the plane, it will give S. The possibility of attacking above the plane is approximately the same possibility attacking from below the plane. Therefore, if this we got it 50%, then most likely we are going to get the other enantiomer with 50%. Now, a mixture of 2 enantiomers with approximately the same percent, we call it racemic mixture. That's why we are going to get it and the same as 2 products and the racemic mixture. Got the question now? Got the point now? Did you get it?
Yes دكتور.
Perfect. Now,
بس
sure.
الحين اللي بس عبالي إنه لما يصير تفاعل مع الهلال
مع إيه؟
يعني مثل البروم أو البرومين أو الكلورين.
Right. It's the same thing. Just ask your question for it. Ask your question.
خلاص تمام.
أكيد.
أيوة شكرا.
All right. Now, you see here, let's talk about the influence of the substrate on the SN1 reaction mechanism. As you can see in this slide, here we have the tertiary alkyl halides way much faster than secondary alkyl halide. And the secondary alkyl halide is approximately the same like the stability, we're talking about carbocation. The stability of the carbocation. Tertiary alkyl halide is more than primary, more than secondary, more than primary, more than methyl. We have explained that before, isn't it? We did explain that the stability of the tertiary carbocation more than secondary, more than primary, more than methyl, isn't it? We did explain this before regarding the stability of the carbocation. Why the stability of tertiary more stable than secondary, more stable than primary, more stable than methyl?
More alkyl group.
Exactly. As the number of alkyl groups increases, simply the possibility for hyperconjugation will be higher and therefore the stability will be more. Like now we will introduce or we will explain the stability of, as you can see here, what we call it here benzylic carbocation and allylic carbocation. Benzylic and allylic, they have approximately same stability like secondary, although this is here, as you can see, this is a primary and this is a primary. Although these two types of carbocation, although they are primary, but they have approximately same stability like secondary. Why? Why is that? Simply, let's talk about stability of benzylic carbocation. The benzylic carbocation, as you can see, is this one, right? This is a special type of carbocation which we call it benzylic. Any carbon attached to benzene here, this position we call it benzylic. So it's benzylic carbocation. You can see here we may draw resonance structures of this carbocation. That the double bond comes here and we can simply have this resonance structure, CH2 and then plus, and then we can continue. You follow me? You may draw it and you can have them there. So due to the resonance structures, the stability of benzylic carbocation almost like secondary carbocation. Although it is primary, like due to the resonance structures which we may draw, then the stability of the benzylic carbocation is the same approximately like stability of the secondary. And this applies also to allylic, as you can see in your slide. So the allylic here, you can see the allylic carbocation is this one. For example, CH2 double bond CH2, then CH2 plus. Here, this is called allylic carbocation, allyl carbocation. Now we can simply draw resonance structures where the double bond can come here, and then we will have it here, CH2 plus, then CH2 double bond CH2. That's actually, this is the reason why the stability of the carbocation is like that. In principle, just to make the story short for this slide, this will give us hint here. It will give us like expectations for the behavior. Generally speaking, tertiary carbocations are the best alkyl halide, the tertiary carbocation which comes from the tertiary alkyl halides. The tertiary alkyl halides are the best, most likely to undergo SN1 reaction mechanisms rather than the methyl or the primary. Do you follow me? So the more stable the carbocation, the more possibility to undergo SN1 reaction mechanism. Let's take it like that. As the stability of the carbocation increases, as stability of carbocation increases, then will prefer to undergo SN1. That's why actually tertiary alkyl halides, most of the time, most of the reaction undergo SN1, not SN2. It is never SN2. Will never go SN2. Most of the time, all of the time, instead there is another competing reaction. All the time it will undergo SN1 reaction mechanism and will never undergo SN2 reaction mechanism. That's actually why, this is why actually we are simply discussing the effect of these factors on the reaction. Is there any question so far? As you can see in this slide, this is the slides or the resonance structures which we may draw for allylic or for allyl carbocation and as well as benzyl carbocation. And these resonance structures will increase the stability, and therefore the stability of these species can be somehow considered as the stability of the secondary carbocation. Any questions so far, guys? Is there any question?
No, Doctor.
Perfect. Now you can see this is simply these are just allylic and benzylic. This is just to show you the breakage of the bond, how much the bond strength of each here. For example, this is normal sp3 hybridized to chlorine. This is all of them sp3 hybridized carbon to chlorine. But here you can see we can break up this bond. If you want to break up this bond, we need 332 kilojoule per mole. But if you want to break the allylic carbon chlorine bond, then the bond energy will be less, 289, and the benzylic will be approximately 293, which is very much less compared to this bond strength. And the reason for that is simply the previous slide. Because when we break up that bond, what we are going to form, we are going to form the carbocation. This carbocation, the allyl carbocation, will be specially stabilized due to the resonance. The same thing applies to the benzyl carbocation, because as you can see, again, we can draw different resonance structures for the benzyl carbocation. That's actually the reason for this type of difference in the bond strength of these carbons. Now, yes, please.
الحين في الكلاس اللي قبل شرحتنا عن الرياكتيفيتي.
Yes.
أحسها يعني تكون عكس
yes.
اللي شرحته.
Right. In the previous lecture, we were talking about another mechanism, which is SN2. Now we are talking about SN1. Remember, now in order not to make any confusion, we have two mechanisms controlling this reaction. Depends on the nature of the substrate. Now we have SN2, which where the SN2, the nucleophile, attacks from the backside, bond making and bond breaking happening at the same time. That's what we called it SN2. And in the SN2, we said as methyl alkyl halide will always go SN2. Methyl is more than secondary. Methyl more than primary, and primary more than secondary, and secondary more than tertiary. Like in here, in this reaction, we are talking about different mechanism. The mechanism here, it's the first step will be the removal. Can you see? Do you see the model here? Can you see the model?
No.
You didn't see my.
بس شوية بتنزل الكاميرا لو سمحت على تحت.
Just a second. Let me just see what's wrong with the camera now. All right. Can you see? Oh yes. No, it's okay. Now you see the camera now, right? Now here in the SN1, the first step will be the breaking. Suppose this is the halogen. This yellow atom is the halogen. The first step will be the breaking up of this bond, and the halogen will leave as X minus. So what's remaining here? It will remain the carbocation. Do you follow me? This is SN1 mechanism. So the SN1 mechanism depends, or the substrate which will undergo SN1, it depends on the stability of this intermediate, because this intermediate is carbocation. When this intermediate, the stability increases, therefore the substrate will undergo this mechanism. If the stability of this carbocation is not good, then this substrate will never undergo SN1. In other words, let's get back to simply the previous slide. In the previous slide, as you can see here, in the previous slide here. Now you see, we have different alkyl halides. The tertiary alkyl halide, when the halogen leaves, it will leave the tertiary carbocation. The secondary alkyl halide, when the halogen break, it will leave secondary carbocation, and so on and so forth. Now, here, this is the most stable carbocation. This is the most stable intermediate. Therefore, we are expecting tertiary alkyl halide to undergo all the time SN1 reaction mechanism, because it will produce a stabilized carbocation, the most stable carbocation. While methyl carbocation and primary alkyl halide will never undergo tertiary, will never undergo SN1 reaction mechanism. They will always prefer to undergo SN2 reaction mechanism. Get the point? Because the methyl and the primary will, when the halide leaves, it will leave unstable carbocation, as you can see. The primary and the methyl, they have very low stability, and therefore the reaction or these substrate will never undergo SN2. They will always prefer SN1. Yani, this side here, this tertiary, always SN2. This methyl and primary always, I'm so sorry. The tertiary always SN1. The methyl and the primary always SN2. That's actually the point here, because we are talking about two different mechanisms, not only one. Do you follow me? Now, regarding the effect of the leaving group, exactly the same. Always the leaving group, or when the reaction becoming faster, when the leaving group leaves faster, and when the leaving group becoming better leaving group, as it becomes weaker base. So this is simply the trend for the basicity. You can see here, for example, the basicity of the OH minus is, or let's start with the water. The water is less basic than this tosylate ion, and the tosylate ion is approximately the same basicity like I minus, and I minus higher, weaker basicity than Br minus, and so on and so forth. So that's actually the point here for the leaving group reactivity. The water is the best leaving group. Then these ions. Do you follow me? So always the leaving group power depend on the weakness of the base. As the base more weaker, it will be better leaving group. That's the whole issue always. Any question? Is there any question about this slide?
What about the rate of reaction?
The same, because simply here, as you can see, the rate of the reaction when the leaving group is water is more than the reaction when the leaving group is this one, is more when the reaction is approximately the same like I, but it is more than bromine, more than chlorine. In other words, alkyl iodide are faster in the reaction in SN1 or SN2 compared to alkyl bromide, compared to alkyl chloride, compared to alcohols, and therefore alcohols will never undergo nucleophilic substitution reactions. Do you follow me? Now, what makes the alcohol undergo nucleophilic substitution? First of all, we need alcohols. We can convert alcohols to alkyl halides. Let me see a reaction like this here, for example. If we want to, suppose, if we want to make nucleophilic substitution with alcohol, suppose CH3OH, we want to allow it to react with nucleophile. Now, what should we expect? We should expect that the nucleophile will displace or will substitute the OH, and then we are going to get OH minus, right? So the leaving group here is OH minus. The question is the OH minus, is the hydroxide here, is it good leaving group or bad leaving group? What do you think? Is the OH minus good leaving group or bad leaving group?
Bad.
Why? Because it is very strong base. Therefore, it is very bad leaving group. Therefore, this reaction will never go. Or unless, at least it's extremely difficult to go unless very, very extreme conditions. Do you follow me? So in this case, the OH here is very bad leaving group. But for example, halogens are good leaving groups because simply they are very weak bases. Why halogens here, for example? But here if we have CH3Cl, for example, or not Cl, even any halogen, and we allow it to react with nucleophile, this reaction very easily go to the nucleophilic substitution, and then we got CH3 nucleophile plus X minus. Why X minus is very good leaving group, guys? Or relatively speaking, compared to the OH, they are good leaving group. Why halogens are good leaving groups? Why? In one word, why?
Because weak bases.
Why halogens are weak bases? Because they're coming from the corresponding hydrogen halide. Hydrogen halide, HCl, HBr, HI, all of these acids are very strong acids. And we said the general rule, very strong acids will definitely form very weak conjugate bases. That's always true. You follow me? So the halogens are very weak bases because they're coming from very strong acids. That's why we all the time consider halogens, and that's the whole chapter is about reactions of alkyl halides. Get the point? Do you follow me? Is there any question? Hello? All right. I just have to move because since there is no response. All right. Now, alcohols can be halogenated. Simply, actually, can be substituted. For example, suppose we have tertiary alcohol here. For example, this here, tertiary butanol. If we allow the tertiary butanol to react with, for example, HCl, what we are going to get, we did discuss this reaction, and we are now going to discuss its mechanism, CH3Cl. As you can see here, plus water, of course. You see, in this reaction, the leaving group here, it's not OH, it's OH minus. The leaving group here is H2O, and the H2O is very weak base. Therefore, we should consider it as, or classify it as, very powerful, very good leaving group. That's the whole issue. Do you follow me? In this reaction, which we have explained it before, this reaction proceeds via SN1 reaction mechanism. Why? Because the first step will be simply protonation, the H plus here. Guys, do you hear me? Just to check out that you are following me. Do you hear me? Can you see the board?
It's not clear. We hear, but we cannot see.
Can you see the board? Do you see the board? Hello? Can you see the board? All right.
Not clear, doctor.
The board is not clear, or it may be the connection you mean?
No, it's clear.
Okay. Now, the alcohol here, as I said, alcohol can react with hydrogen halides to produce the corresponding alkyl halides and water. As you can see, this is substitution reaction, but in this substitution, this is very special substitution reaction. We have H2O here leaving, not OH minus. In this case here, in this case actually, the H2O here is very powerful leaving group because it's very weak base, as you can see in the slides there. Do you follow me? So what's the mechanism? What's the reaction mechanism? The reaction mechanism is SN1. As you can see in here, I'm just in order not to repeat the same what you have it in the slide, let me just go through the slide again. Do you see the slides here? Can you see the slides? Do you see the slides?
Yes.
All right. Can you see here? First of all, there will be protonation of the OH, and then the OH becoming OH2 plus. Then the water, it will leave as H2O, leaving the carbocation. Then the Br minus will attack the carbon, and then we will have simply the alkyl halide. Let me just write it again. Now, first of all, the H plus will add itself. The lone pair here will be given to the H plus, and then we'll get here CH3, 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 OH2 plus. Then here, this will leave as OH2 plus now, not as OH minus. We will get then the carbocation, the tertiary carbocation, which is highly stable. And then finally, the Cl minus, which present in the reaction mixture, will attack in here, and it will give simply the plus in this case, and the alkyl halide. So the alcohol generally, as we said before, alcohol can react similarly and can simply give the alkyl halide because they will proceed via SN1 reaction mechanism. So as you can see in this slide, there is no effect, there is no difference in the rate if we use HBr or HCl or HI, because the intermediate all will proceed via tertiary carbocation, because regardless of what alkyl halide what hydrogen halide we are using, the intermediates are the same. Since the intermediate is the same stability, then most likely the rate of the reaction will be almost the same. Do you follow me? I'm going to skip this slide. Now, and I'm going to skip these two slides, please. Slide 34, slide 35, skip them. All right? We'll just move to elimination reaction. And actually, I would prefer to stop now because it looks like there is some problems in the internet. I will simply finish this elimination reaction and the whole chapter next Monday, and then we can continue just to make it as one pack of discussion rather than to disconnect it into twice. Do you follow me? So before talking about the elimination, we're done with the substitution. And to make the story short, you hearing me, guys? Do you hear me? Do you see me? All right. Now, to make the story short, before going through the elimination, all what you have discussed today, in the morning and now, we discussed that there are two reactions. We are talking about a reaction which is called nucleophilic substitution reaction. I'm just trying to make a summary of the most important aspects of all what we have learned today. So we have alkyl halides here. This is alkyl halide reacting with the nucleophile. Nucleophile can attack and then the halide leaves. Here, this halide which will leave, we call it leaving group. Why this reaction takes place? Because these halogens are good leaving groups, and why they are good leaving groups? They are stabilized. They are, we call them weak bases. Always the weak bases are the stabilized one. You follow me? So that's the whole issue. Now, how the reaction, the details of the reaction, how the reaction works, this is actually what we have said is the mechanism of the reaction. We have two mechanisms explaining this reaction, the nucleophilic substitution. Yani, regardless of the outcome, always the outcome will be the same. If it is SN1 or SN2, always regarding the nucleophilic substitution, we will get the same product. But the mechanism is different. For example, some alkyl halides may undergo what we call it SN2 reaction mechanism. What's the SN2 reaction mechanism? The SN2 reaction mechanism, it involves the attack of the nucleophile, suppose this is the nucleophile, opposite to the halogen, and the halogen here, I assume it's the yellow one. So it will attack from the back side, all right? Start to bind itself to the carbon, and this halogen start to break the bond between the carbon and the halogen. You follow me? Until a certain point, the nucleophile will fully bond it to the carbon, then this will leave fully, and therefore we will get the product. Now here, that's why, first of all, two aspects. First, since this will attack from the back side, we will always get what we call it inversion of configuration. For example, if this is R and this attacks from the opposite side, we are going to get S configuration. Because as I said, maybe with my hand is better. Suppose this is the umbrella, this is how the tetrahedral, and the yellow one here is the above the plane. You follow me? Now when this comes from below, becomes like that, this umbrella goes up like this. So which means we have got inversion of configuration, or the configuration of the product has been inverted. To make the story short, simply, if your stereocenter of the alkyl halide is R, your product will must be S. If it undergoes SN2. You follow me? And vice versa is true. If you started with R, you get S. If you started with S, you get R. Always, this is characteristic of SN2 reaction mechanism. Now, since the reaction, this SN2 reaction mechanism, it involves the attack or formation like 5 bonds here, you follow me, and attacking from the backside. These groups here, if they are hydrogens, this nucleophile easy to go. But if this is a methyl, for example, there will be somehow some sort of steric hindrance. There will be some sort of repulsion between this coming nucleophile and this existing group. But imagine if you have methyl here, or R group here, R group here, R group here. This reaction will never undergo. That's why tertiary alkyl halide will never undergo SN2. That's why the rate of the reaction will be always the methyl alkyl halide will be very much higher in rate compared to the primary alkyl halide, compared to the secondary alkyl halide, compared to the tertiary alkyl halide. That's all about SN2 reaction mechanism. Now, there is another mechanism which explains the nucleophilic substitution, in which instead of the attack and the breaking at the same time, in here we will have two-step reaction mechanism. The first step, the halogen will leave fully, the bond will break up, and then we will get what we call it a carbocation. And remember, the carbocation is somehow, planar, like this. And simply we will have like a p orbital above the plane and below the plane. Now, when the nucleophile, the second step, will attack, it may attack from both sides. It may attack from above the plane or from below the plane. Each attack will give, if you have a stereocenter, you will get absolute configuration. So you will get R and S at the same time. Therefore, SN1 reaction mechanism always occurs with what we call it racemization. Another aspect, since all SN1 reaction mechanism involves the formation of the carbocation, then definitely the rate of the reaction will depend on the stability of the carbocation. That's why the slide which we have explained before, the slide when we compared the relative rates of the carbocation or the stability of the carbocation, here, this slide here, you can see these alkyl halides, the tertiary alkyl halide is all the time will react via SN1, while the methyl and the primary will never react via SN1 reaction mechanism. With this summary, I think it's enough for today. We can stop this lecture, and inshallah, next Monday we will continue the remaining of this chapter, and then in the evening on Monday we will finish, or we'll start at least chapter 15 in order to finalize everything, or to try to finalize, inshallah, everything before the end of the next week. Is there any question before leaving? Is there any question, guys? Okay, thank you very much. I wish you all the best today. Inshallah, I'll meet you on next Monday, inshallah. Thank you. Have a good day. Bye-bye. Orbital, we have PR loop above the plane and loop below the plane. When the nucleophile attacks, it may attack from above the plane or from below the plane. Therefore, the possibility of attacking above the plane is exactly like the possibility of attacking below the plane, and therefore we will get like two stereo configuration. That's why we call it racemization, R and S, instead of one stereoisomer like SN2 reaction mechanism. With this introduction, I will stop for today, for this lecture, and then inshallah we'll continue our lecture in the lab time at 2:15, so please be there on time. Is there any question before leaving? Is there any question about SN1 reaction before leaving? Alright, then inshallah, as I said, we will meet at 2:15, and we will try to continue this chapter. If not, then maybe slides remaining, we will continue it on Sunday. I wish you a good day, and inshallah see you at 2:15.